Welcome to the mini course in dynamical system approach for Lane-Emden type problems. This is our second lecture, and the idea is to detail some of the things that were presented in the first lecture of our mini course. So we start with the classical Lane-Emden equation, Laplacian of u plus modulus of u to the p minus 1 u equals to 0 in omega, domain in Rn, u equals to 0 on the boundary of omega, where p is positive bigger than 1, and we look for radial solutions of this equation, changing the variables to radial variables, we get the equation in the radial form of the Laplacian u2 prime plus n minus 1 r u prime equals to minus u to the p. If it's a regular solution, we're going to assume that u of 0 is gamma positive and u prime of 0 is 0. An important information from this equation is on the Hessian matrix at R for a solution U of the problem. The spectrum of the Hessian matrix is going to be U2 prime and U prime over R, as it says in the following lemma. If U is a radial C2 function, the eigenvalues of the Hessian matrix D2U are given by U2 prime, which is simple, and U prime of R over R with multiplicity n minus 1. It's proved by calculations, but we have included it here in order to give a taste of this fact. We write u of x as phi of r, a function of r, where x is a vector in Rn, and we are going to prove that the spectrum of the Hessian matrix at x is the enopole in red. First, take the derivatives with respect to xi. So u derived with respect to xi is phi prime in r times xi divided by the norm of x. So this gives the gradient of u in x as phi prime of r over r times x. And take second derivatives because we're going to approach the Hessian matrix. Second derivatives u xi xj is at x is the sum of three terms. Phi 2 prime at r times xj xi divided by r squared plus phi prime of r delta ij over r minus phi prime of r xi xj divided by r to the third. Calculations, putting all together, we get that the Hessian matrix of u at x is given by phi 2 prime at r times the tensor x by x divided by the norm of x2 squared plus phi prime of r divided by r times the matrix identity minus tensor xx divided by modulus of x squared, where tensor of c vector is the matrix with entrances xi, xj. So on this notation, if we apply this D2U matrix to the vector x over modulus of x, we end up, after some calculations, getting phi 2 prime of r times x over modulus of x. Therefore, phi 2 prime is the eigenvalue with associated eigenvector x by norm of x. And if you multiply the Hessian matrix D2 of u at x by xc vector, which is orthogonal to x, we get, after some calculations, that phi prime of R over R times C is the Haitian matrix D2U at X times C. Therefore, phi prime of R over R is also an eigenvalue associated to the eigenfunction C, n minus 1 of this type. So that's how we prove that we have this spectrum for the Haitian matrix of U radial. Now, going forward with the weighted problem, if we put the weight modulus or norm of x to the a in front of the nonlinearity, we get what we call the unknown Lane-Emden equation. For a bigger than minus 1, we are going to consider this problem, and radial solutions of this equation are simply solutions of this ODE, nonlinear ODE. But if we change variables to R s to the k, big U s equals to k to the a times U r, then we get the following equation. U2 prime plus n hat minus 1 over r u prime equals to minus U2p. So this is a Lane-Emden equation with an effective dimension. In place of n, we have this n hat after you substitute this and do the calculations. So we are able to go back and study Lane-Emden equation with a dimension-like number in front of U prime. Now, taking more general operators like Pucci's operator, which is m plus minus lambda lambda of dtu, plus a weighted nonlinearity modulo norm of u of x to the a, u to the p. This is a fully nonlinear equation with a Pucci's operator, involving Pucci's operator. We're going to study this for a bigger than minus 1, p bigger than 1, and lambda small less than equal to lambda large. The Pucci's operator is defined in terms of the eigenvalues as the sum of large lambda times the positive eigenvalues and small lambda times negative eigenvalues, where these are eigenvalues of the matrix X. That's why it's important to understand the eigenvalues of this Haitian matrix in order to know what expression we are using for Pucci's operator. So when we study this problem and omega is a bounded domain, we're going to assume the Dirichlet condition on the boundary, u equals to 0 on the boundary of omega. But the Pucci's operator is given by this sum. If lambda and lambda are equal, then you have a multiple of the Laplacian operator. But if not, what we need is to know when the eigenvalues are positive or negative. In case we're looking for radial solutions, we have shown before that the spectrum of the Haitian matrix is given by this eigenvalue and the other U prime over R eigenvalues. So we know how the Pucci operator is stated in terms of these eigenvalues for radial solutions. So when looking for radial solutions of the Pucci's operator, the expression of the operator becomes a lot more tractable. and it's going to be m plus u2 prime n minus 1 over r m plus of u prime equals to minus r to the a up, and depending on the sign of this u prime and u2 prime, you have the expression lambda s for s less or equal to 0, or big lambda s for s bigger than 0. So depending on the sign of the eigenvalues, you know what expression you're dealing with. Another way of writing the Pucci's operator is u2 prime equals to m large M plus, where large M plus is given by S over small lambda for S negative, or S over large big lambda if S is positive, times this expression, and inside these parentheses, the M plus is going to depend on the sign of U prime, and therefore the sign of these eigenvalues. So we can write U2 prime in this very simple form, coming from Pucci's operator in the radial setting. Radial domains which are tractable are the ball, the anannulus, Rn, and the exterior of a ball. It's not difficult to see that the solution U is decreasing with R for omega ball or Rn. So the equations become depending only on the second derivative and on the sign of the second derivative, because the sign of the first derivative is already negative and you have the expression of small m plus. But for m plus in u2 prime negative, this is going to be the small lambda multiplying this negative eigenvalue. And for u2 prime positive, the Pucci's operator is going to be big lambda multiplying this positive eigenvalue. So we arrive at these two very easy expressions for the Pucci's operator once we know the sign of the first derivative and the sign of the second derivative of u. If you divide by small lambda, big lambda, and everything, we arrive at these dimension-like numbers in tilde plus, given by this sum, which is less than or equal to n, and n tilde minus, given by this sum, which is bigger or equal to n because of this ratio. These dimension-like numbers play an important role, as we are going to see, and they were already identified at the work of Cutri-Leone 2000 on existence and non-existence of super solutions for the Pucci operator, and Quas-Sirakov for existence of solutions in not radial. So back to the Pucci's operator M plus, we have the weighted problem here stated for Rn, or Rn without the origin. If it's without the origin, we are thinking as the limit as R goes to 0 of the solution is plus infinity. These are going to be singular solutions. And we associate to this Pucci plus equation other variables, and we are going to associate to our ODE problem a system of ODEs on new variables. We define the variable x of t as minus r u prime over u, and z of t as minus r to the 1 plus a up over u prime, for t the logarithm of r. With these two new variables, we can take the derivative with respect to t, and using the equation in the radial form, obtain the following dynamical systems. X dot, which is the derivative with respect to t, is equal to this expression in powers 2 of x and xz, and z dot is equal to z times this expression. This is obtained by using the radial expression of this Pucci's equation. Let's see how. Okay, before that, defining these two variables x and z, we can take the phase plane xz in R2 and study the solutions for this dynamical system. Since we are studying positive solutions, the points z, x, and z belong to the first quadrant when u prime is negative, or to the third quadrant when u prime is positive. We denote the first and third quadrants as 1q and 3q, respectively. They are given here. And as a consequence of this monotonicity, we have that problems Pucci plus and Pucci minus in the radial setting for Pucci plus is given by this expression. Why? Because u prime is negative in the first quadrant, and is given by this expression. Why? Because u prime is positive in this expression, because u prime is negative in the first quadrant. In the third quadrant, it would be the opposite. How do we derive the dynamical systems? Just as an example, an illustration, take the expression with Pucci's operator in the radial form in the first quadrant. We have this expression. Take the variable r with respect to t, it's e to the t. The derivative of r with respect to t is r itself. So when we take the derivative of x with respect to t, we have this expression, derivative with respect to t, but then we exchange this into derivative with respect to r, and we have this expression. Now we can substitute u2 prime by its expression, which is here. We substitute u2 prime, and we put all these expressions in terms of x and z, and we obtain the equation x dot equals to x times m given in terms of z, plus x2 plus x. And this is the first equation in the dynamical system. If u prime is negative in the first quadrant and m plus is 1 homogeneous, all this was used to deduce this first equation in the system of ODEs for x and z. We can do the same for x in the other quadrants and z in the first and third quadrant. So anyways, we arrive at these dynamical systems associated with the equation we had. This corresponds to p plus for m plus, and the dot stands for the derivative with respect to t. Now we start studying the dynamical systems itself in order to get information to solve our Pucci's operator problem in the beginning. So, concavity regions of U. Note that the expression we have is U2 prime given by this expression for Pucci plus. But in the first quadrant, this is equal to 0 if and only if what you have inside is 0. But then when you put the equality, this equals to 0, you get that z is the line, horizontal line, lambda n minus 1. So this is where we are going to have a change of concavity. For z bigger than lambda n minus 1, we are in the region where u is concave. And for r negative, z less than lambda n minus 1, we have that u is convex. So we divide the phase plane in two regions, up and down, depending on the concavity of u. This for the operator m plus, the same with opposite lambdas for m minus. But okay, the dynamical system given in terms of an f function xz and a g function xz is this one. These functions change depending on the m, and the m changes depending on the concavity of u. So each one of these has a different expression depending if you are in the region r plus or r minus in the xz plane in the first quadrant. The same for g. G has two expressions depending if you are up and down with respect to the horizontal line z equals to lambda n minus 1. This is going to be important in order to write explicitly this expression in the dynamical systems, depending if you are above or below the horizontal line z lambda n minus 1. Again, the dimension-like numbers come into play in these expressions you see here in tilde plus and tilde plus. And we are going to work with in tilde plus bigger than 2 in the whole setting. So after identifying the horizontal line which separates the phase plane into two regions of concavity, we go forward in the study of the stationary points for the dynamical systems. So in order to study the stationary points for the dynamical systems, we have to see where z dot is 0 and x dot is 0. In the first quadrant, for example, we have this line, which is z equals to a constant minus lambda x, where x dot is 0. And this is going to be in the first quadrant. And for z dot equals to 0, we have two different lines, one in the region of concavity above and one in the region of concavity below. Z is equal to a constant minus p of x in the region above, and another constant minus p of x in the region below. But these three lines are going to be decisive with respect to the flow defined by the dynamical system. This is a picture of the important lines. This red line is the line of concavity. Above, you have region r plus lambda. Below, you have region r minus lambda. The blue lines are the two lines for z dot equals to 0, and the green line is the line of x dot equals to 0. So this is what is nice studying the Pucci's problem in the dynamical system approach, because the important things with the flow happen when they cross these straight lines. So it's easier to see what's going on. Once we have the lines where z dot is equal to 0 and x dot is equal to 0, we can identify stationary points. They are the points where these lines cross and where the lines cross the axis, because at the axis we also have z dot equals to 0 and x dot equals to 0. So when we identify the crossing, we arrive at these 4 points. 0, 0 is a stationary point. Then we have n0, which is in the vertical line of the first quadrant. A0 is in the horizontal line, and M0 is a point with entrances not 0, x0, and z0. X0 is alpha, 2 plus a p minus 1, and z0 is the sum of this number and depends on p, which is going to move the point m0 depending on p. On M minus, you do the same study, find the lines, cross the lines, and obtain the stationary points. Crucial marks which appear when we do all these calculations are some p's and the alpha that we saw before defining M0. Alpha is 2 plus a over p minus 1, and we have 3 different p's for plus and other 3 for minus, defined as you see in these expressions. The PPA, PSA, and P delta A are going to be very important in our whole study. Again, the dimension-like numbers appear to define these P numbers. We are going to see how they come into play. A theorem about these stationary points, the local study. The origin is a saddle point. The stable and unstable directions of the linearized systems are x and z axis. So from 0, 0, we are going to see lines exiting in the vertical direction and arriving in the x direction because of this statement. N0 is a saddle point. The tangent unstable direction is parallel to this line. Z equals to minus a constant times x. So orbits exiting N0 are going to be tangent to this line, which has a negative slope for M plus, and this line for M minus. And at N0, there is a stable manifold, which is the vertical line. Points at the vertical line arrive at N0 as time goes to plus infinity. A0, what type of stationary point is A0? A0 is a saddle point for P bigger than PSA. The linear stable direction is parallel to this line, which is a line Z equals to minus a constant times X, which means has negative slope, and it's the line pointing to A with this slope. In the case of M plus, the same for M minus. While the unstable tangent direction lies in the x-axis. Therefore, at the x-axis, the orbits exit A0. For P less than PSA, A0 is a source. And at PSA, A0 coincides with M0 and belongs to the x-axis. We're going to see in pictures how it goes in this case. In this case, it's not a hyperbolic stationary point, and A0 is going to be a source like M0. What happens to the fourth stationary point? It depends on the P. If P is less than PSA, M0 belongs to the fourth quadrant and it doesn't correspond to positive solutions. So we are not going to be interested in this situation. P belongs to the first, M0 belongs to the first quadrant if and only if P is bigger than PSA. But in this case, you have ranges of P where M0 changes its character. M0 is a source if P is between PSA and PPA, is a sink for P bigger, larger than PPA, and is a center exactly at PPA. So M0 is a stationary point that changes a lot with respect, depending on the P of the nonlinearity of this problem. Okay, how do we prove this theorem? The proof is based in the linearization of the operator around these stationary points. So we linearize the system of ODEs that we have, and the linearization at any point xz is, here is the derivative of f with respect to x, the derivative of f with respect to z, the derivative of g with respect to x, and the derivative of g with respect to z. F and G were given by the second order expressions before. Okay, this when the point xz is in the upper half of the first quadrant. And if it's in the lower half, then the expressions of f and g change, and you see n tilde in the place of n. Now, since we have the linearization of the system in any point, we apply to N0 and A0, and we get the following matrices. For Ln0 is this matrix, and La0 is this matrix. Just substituting these values in the expressions, depending, N0 is in the upper half, the upper part of the first quadrant, R plus, and A0 is in the lower part. So substituting, we get the two matrices which represent the linearization around these points. Now we study using this linear matrix, we study the eigenvalues of the matrix, which are going to be the eigenvalues of these stationary points. The eigenvalues for N0 are 2 positive and minus n minus a negative, which means that N0 is a saddle point. There is a stable manifold with this eigenvalue associated, and this is the vertical axis, and an unstable manifold with this eigenvalue associated, which is the one in corresponding to the other direction. The eigenvalues for A0 are sigma 1, given by this difference, and sigma 2, given by this sum. And at M0, we have to work a little bit more in order to find the eigenvalues and eigenvectors. We take x0 from its expression, z0 from its expression, substitute in the matrix, and we analyze the eigenvalues of this matrix on the characteristic polynomial given by this polynomial. And depending on the roots of this polynomial, we have the eigenvalues for the stationary point M0. So we end up with different roots or zeros depending on this delta given by this number, all obtained by calculations substituting the values x0 and z0 in this matrix. But summarizing everything, we have x0, z0 over lambda equals to alpha and tilde minus 2 over 2 for p equals to ppa. So the real values of the sigmas in the characteristic polynomial are 0 and the roots are purely imaginary in the case p is equal to ppa. In the other cases, for p less than ppa, we have this comparison, and for p bigger than ppa, we have this order. And if the imaginary of sigma plus minus is different from 0, this already determines the sign of the two roots of the characteristic polynomial. Assume the imaginary is 0, the zeros, the roots of the characteristic polynomials are real, you have real eigenvalues, and then we can study what happens to M0. In the first quadrant, the first situation, this situation is going to give that if sigma plus minus are positive, M0 is a source. And this happens in between PSA and PPA. For any P in this range, we have the roots are positive, the eigenvalues are positive, and M0 is a source. On the other hand, if P is bigger than PPA, then you have negative roots and M0 is a sink. So after in some specific calculations, we end up identifying all the possibilities for the stationary point M0. Anyways, this is a picture. Here is the stationary point N0. The vertical direction is stable, and this is the direction, unstable direction obtained in the theorem. A0, the horizontal line is unstable, so all the trajectories exit A0, and there is a direction which has negative eigenvalue, and this eigenfunction, let's say eigendirection, points towards A0 in the stable manifold, in the stable line. At M0 depends on P, if it's going to be a center, source, or a sink. And 0, 0 is just a trivial stationary point where the horizontal line is stable and the vertical line is unstable. What happens, for example, when P is less than PSA? In the first quadrant for Pucci plus operator, we have two possibilities. P equals to PSA, then you have M0 and A0 coinciding as the same stationary point. And when P is less than PSA, M0 is going to be in the fourth quadrant and is not going to be a stationary point for positive solutions. Only A0 is a stationary point in these axes. So these are different behaviors of the stationary points depending on P, and were obtained in the proof of this theorem. Thank you for your attention, and we hope to see you in the next lectures.